Thank you for coming today. Great pleasure to have you all today in the first session of this of our fourth consecutive edition of year of the TSMS seminar. So today we have the pleasure to listen to Emeric Roulley from CISA. So Emeric, he did his PhD at in France, in Rennes, with Tawfiq Hamidi, and currently he's working as a postdoc in CISA. So Emeric is going to talk about vortex patch motion in bounded domains. It's all yours, Emeric. Thank you.
Thanks, Aaron, for the introduction and for the invitation for this online seminar. It's a great honor for me to be here. So, as Harun said, I will speak about vortex patch motion in bounded domains, and more precisely, the construction of periodic vortex patch motion, periodic in time, in bounded domains, which are quite general, simply connected bounded domains. But first of all, for this particular seminar, we should first give an introduction to the field, so that we can explain everything, starting from the really beginning, and then to arrive to our result, which has been done in collaboration with Zineb Hassania and Tawfiq Midi, who are in Abu Dhabi. So the plan of the talk is the following. We will introduce the equation of motion for a fluid, which are the so-called incompressible Euler equations. So these are partial differential equations describing the evolution of a fluid. And for these kind of equations, we have particular solutions which are given by vortex patches. So we will introduce this notion and describe a bit the previous literature about periodic so-called rigid motion. I will describe it later. Then we will discuss about more formal solution to the Euler equation, which are the so-called point vortices. And then we will discuss again the literature related to the periodic rigid motion. And we will introduce our main results, where we, in some sense, extend the previous literature to the periodic non-rigid motion in bounded domains, and discuss, of course, the proof of the main results. So let's start. So we consider a fluid in R2. So to describe the fluid, Euler introduced in 1755 the following equation, which is basically the Newton law applied to the fluid. So U is the velocity field. So you describe at any time and any position x. You take a mesoscopic volume of fluid, and you make the average of the fluid particles there, and it gives you the at the time t and position x the velocity, an average velocity for the particle located there. And since you can do it in any point, this gives you a velocity field. You also have the pressure at any time and any position, called P of t, which is a scalar. And the equation is this one. Then Helmholtz has introduced a quantity called the vorticity, which is defined by this expression, and which describes the local rotation of the fluid, because this is so-called rotational of the fluid in 2D. So in 2D we can so this quantity is a scalar, or identified to a scalar, and solve a transport equation of this type, where U is the velocity field again. And we make the assumption that the fluid is incompressible. So mathematically, it's translated in the fact that the divergence of the velocity field is 0. And since we are in R2, and in particular in a simply connected domain, we can write U as the grad perp of function psi, which is called the stream function. And grad perp is defined as the rotation of pi over 2 of the gradient operator. So to these kind of equations, we would like to find solutions and discuss the so-called well-posedness, namely, if you give an initial condition in some functional space, does this solution exist, at least for a short time, in the same functional space, or for all time in the same functional space, or you can also ask other questions. And one of the results in these directions, one of the first results, is due to Kato, who proved the well-posedness in HS for S sufficiently large. But there is also many other refinements of these results. I wanted just to cite one, but we will see another one later due to Yudovic. So before this, I would like to discuss what happens if we are not in R2, but in a bounded domain, let's say, or simply connected bounded domain, because this is what will be important in the sequel. So basically, so in R2, you also have that the stream function solves this Poisson equation, where omega is again the vorticity. But you ask also a Dirichlet condition for the stream function if you are in a bounded domain, so that you can have a good well-posedness theory. And the equation are these ones. The stream function psi can be recovered from the vorticity omega by inverting this relation, so inverting the Laplacian. And in general, you can write psi as the integral of the omega against a green kernel, G of D. And the green kernel is given by this quantity. So phi here is the Riemann mapping. So if you take your domain D, you make a conformal transformation to the unit disk. And then you can express the green function like this. So the kernel is quite explicit in some sense if you know the Riemann mapping. So this kind of transformation here for people doing geometry is quite like you can recognize it as the link to the Mobius transform and stuff like this. We will discuss a bit more about it later. But here you see that you can really encode the geometry of the domain D into this kernel here. So this green kernel, actually, you can write it in another way, introducing the function k here. And this g is actually the log plus a smooth function k, given by this expression. And in particular, in the case R2, I wrote here bounded, but you imagine what it means in R2. Actually, the k here doesn't exist. So you see that the green function here is just a smooth perturbation of the one in the full plane. So now let us discuss about the notion of vortex patches. So Yudovic proved that if you take an initial condition omega, so you consider the Euler equation for us in the sequel will be this transport equation in R2, and this transport equation in so the same one in a bounded domain, but with this extra condition. So if you take an initial condition omega 0, which is bounded and integrable, then you will have a unique solution. So the existence of a unique solution globally in time, so it will live for all time. And in particular, if you take the initial condition omega 0 to be the characteristic function of some domain D0, so this is my initial condition for omega. I have 1 here and 0 outside. Then for later time, the solution will be of this form. It will be 1 here and 0 there on a given domain dt. And how do I get the domain dt? I take just the image of the initial one by the flow associated to the velocity field. So grad perp of psi, I recall that it was the velocity field. So here you have a complete description of the motion, provided that you know how to tackle the dynamics of the boundary, right? So how do you describe the dynamics of the boundary? Well, you take a parameterization of the boundary, and then if you insert it in the Euler equation, you find that these parameterizations should solve this equation. So what does this equation means? It means that the velocity of a particle at the boundary must coincide with the velocity of the boundary itself in the normal direction. So if a particle is at the boundary here, it should remain at the boundary. So this kind of equation is really classical when you have a free boundary problem. For instance, for the water wave, you have also the same kind of phenomenon. And so this equation is called the vortex patch equation. And this is the equation that we will have to solve to understand the dynamics of a vortex patch. So Udovich proved the result in R2. And there are some refinements, of course, when you take L1 in LP also, instead of in L infinity. But in what we are discussing now, L infinity is enough. Oh, sorry. And but in bounded domains, the Udovich theory can also be proved. And for instance, for the existence part, it is due, the most general result is due to David Gerard-Varé and Christophe Lacave, where basically there is no assumption on the regularity of the external domain. Yeah, this I should mention that, okay, we have a domain D, where the fluid lives, and the solution, which is a patch, is a domain inside the global domain D, and it evolves in time. But for the uniqueness part, it's a bit more tricky for the Udovich theory. You should add some assumptions on the domain. For instance, in the work of Christophe Lacave and Zlatos, they impose some conditions, for instance, that the angles of the boundary should have finitely many angles less than pi or something like this, to have the uniqueness. Also, I want to mention that result due to Ann and Zlatos proved that if you have your vortex patch initially, which is inside the domain D, so it doesn't touch the boundary, then for all time, it will stay far from the boundary, and you can control from below the distance between the boundary of the external domain and the boundary of the patch. And it's a bound like double exponential, like this. Also, I mentioned the result of Chemin, Bertozzi, Constantin, where they proved that if the regularity here of the initial domain, of the initial boundary of the domain D0 is Holderian, like C1 plus alpha, then it should remain C1 plus alpha for all time. So they proved this result in R2, and Nicolas Depot proved it in bounded domains. Okay, so in the sequel, we will discuss the previous literature about periodic vortex patch. So people like this, but who are periodic in time. And in particular, we will look at the domain dt, which is just a rotation of the initial one around the center of mass of D0. So you take D0, you take the center of mass, and you just look for a rotation of it in time. So this is the ansatz. You take your solution with the domain dt, which is a rotation at speed omega of the initial domain. Such solutions are called V-states. And it is not clear at all if such solution can exist or not. And Actually, I should mention that if you take, for instance, Euler equation in R2 is invariant by rotation. If you make a rotation in R2, you don't move the plane. Basically, it's the same. So any radial solution will be a solution because also the Euler equation are invariant by rotation in that case. So you can see it here, for instance, if you have the green kernel here, if I multiply x and y by exponential I theta, I can factorize here and it doesn't change the green kernel. So it's invariant by rotation. So it means that any radial profile will be a solution. And in particular, it will a radial profile is a rotation of itself with any omega. And so it is a solution of this form. So any radial profile that I can give to you will be a stationary solution or trivial solution for any omega. And okay, if you take an ansatz of this form and you insert it in the vortex patch equation here, well, basically you can kill the time because of this omega here and this scalar product there. There is a cancellation of the exponentials, and you recover just a functional. You are led to solve a stationary problem, and the vortex patch equation just become to solve the vortex patch equation just becomes the fact of searching for the zeros of a functional f, which is time independent, but which will depend on omega and on f, which will be, in our case, for instance, small perturbation of the radial profile. So you have the radial profile and you introduce a quantity f, which will be a perturbation of it. And so when f equal to 0, you have no perturbation. So you have the radial profile, which is a solution for any omega. So you have this one and this equation, which is true for any omega, f of omega of 0 is 0. So if you draw what it means, like for any omega, so I can draw a line. For any omega, 0 is a solution. So I have a line of trivial solutions. And there is a result due to Crandall and Rabinowitz of so-called bifurcation theory, which tells you that some conditions such that you can find non-trivial solutions. So I recall I have a line of trivial solution. Imagine I linearize at a point on this line, and the linearized operator is an isomorphism. Then the implicit function theorem tells you that locally the set of solutions of this equation will be like a graph of a solution of a function, sorry. So the trivial curve that we have is the only one because we already have a graph, a trivial line. So if you can apply the implicit function theorem here, it means that basically you just have the trivial solution. So you're looking for properties of the function such that the hypothesis of the implicit function theorem fails. And how can you fail the hypothesis of the implicit function theorem? But not to have an isomorphism, for instance, you need a kernel of dimension 1, for instance. If you have a kernel of dimension 1, in particular, you're not injective, so you cannot be an isomorphism. And the theorem here tells you that if your function is smooth enough, let's say C1, you have a line of trivial solutions, you have a kernel of dimension 1 for the linearized operator at the trivial solution. And so for a given omega 0, this happens. And imagine that the range, so the image of the linearized operator, so the same one, is closed and of codimension 1 in the n space. Then what is the drawing? You have a kernel of dimension 1, you take its complement, you have an image of codimension 1 and the image. So basically, I will send the orthogonal of the kernel to the image because a linear operator realizes an isomorphism from a complement of the kernel to its image. And then what remains to prove is that I can send the kernel to the dimension 1 complement of the image because it's of codimension 1. And to do this, you need this assumption if you do the computation, which tells you that if you take the differential respect to the variable, the second variable, the differential respect to the first variable at my point, and I apply it to the generator of the kernel. If this is not in the range, then I can send the kernel to the orthogonal of the image, let's say. And I can complete everything with the implicit function theorem twice, and I can find another curve of solution because I can apply twice the implicit function theorem. So this theorem tells you that you can find next to your trivial line of solution another line which crosses at omega 0. So the literature that I will discuss now is just an application of this theorem to find a non-trivial curve of solutions, which is different from the trivial line. So the first result in this direction is due to Bourbea. So you take, as we said, any radial profile is a solution. So I take the simplest one, the unit disk. I take the unit disk. So my patch, the trivial patch, is a disk. So for any omega, it rotates. And if you take these omegas, then you are able to find new branches of bifurcations. Okay, you are able to find these solutions. So this tells you that you can construct solutions to the Euler equation in the vortex patch class, which are non-trivial. And actually, what is the shape of this solution is something so-called M-fold. So here you have a 3-fold patch, 4-fold patch, and you imagine for 5-fold, 6-fold, etc., etc. You can do it for any symmetry. And for any M, corresponds one symmetry. So for M equal 2, for instance, you bifurcate from this point, 1/4, and you have a branch of solution with symmetry 2. So basically ellipses, which is known in the literature before as the Kirchhoff ellipses. Then if you take M equals 3, you have another curve, and M equals 4, etc., etc. So this is how you find new non-trivial solutions from a so-called trivial stationary state. And from this, you have a lot of questions which occur that you can ask, right? For instance, what is the regularity of the boundary of the new solutions? Like, what is the regularity of this domain? And this has been proved in this series of works. Like here, they prove that they are C-infinity, and here they prove that actually they are analytic. And as you can see here, the numbers here are between 0 and 1/2. So you can ask, if I take another omega, can I find other non-trivial solutions? And the answer is no. And it's proved in this series of work and indeed in the last one 4 years ago, which tells you that basically if you take omega, so the speed of rotation, which is outside the 0, 1/2, then all patches must be radial. Okay, and the construction of the curve here. So the conclusion of the theorem is locally near the point here in the abstract space. So you can ask also if you can find so-called large amplitude solution, because if you are near to 0, so F is near to 0, and I recall that F was a perturbation of the trivial solution. So if you're a perturbation, you will have small amplitude, right? So you can ask if you can find large amplitude solutions. And this you can get by the global bifurcation theory that I did not present here, but it's another theorem in this area of the so-called bifurcation theory. So you can check the hypothesis of a certain theorem, and you can actually have a prolongation of the curve here. So this is the work done by Hassania, Masmoudi, and Wheeler. And numerically, what you can see is that you follow the branch. So the branch is well defined, and you can follow the branch with a one-dimensional parameter S, let's say. So when S tends to infinity, because this work tells you that you can define it until S infinity. What happens at the end, right? And numerically, you observe that the patches at the end of the branch should have corners of angle pi over 2, like this. And it has been proved really recently by this work of the Chinese group. Okay. So before I took the unit disk, but you can take an annulus, for instance, which is also a radial solution. So it has been analyzed by De La Hoz, Hamidi, Matteo, and Verdela, who proved that you have not just for one symmetry, not just one bifurcation point, omega m, but you have two of them. And in this work, Hamidi and Renaud proved that actually sometimes you can have the local curves which merge to form a loop like this. Okay. In the sequel, we will also discuss about the Euler equation in the unit disk, because everything that I've said until now, so these slides here and the beginning of this one is in R2. But our purpose later is to be in a simply connected bounded domain. So I should mention at least what happens in the unit disk. In this case, you can also find bifurcation points, so curves on non-trivial solutions, emerging at these velocities. So it's just a little shift of the frequencies in the full plane, where B is, so you have the unit disk where the fluid lives, and you take an inside disk of radius B, which is also radial, and you bifurcate from this disk. And these are the bifurcation point for a given B. So everything that I've said until now is based on the fact that Euler equations are invariant by rotation, but they are also invariant by translation. And so if you, for instance, periodize in the x variable, you can prove. So this is a work that I almost finished. You can prove that you have also bifurcation from what are the analogues of the trivial solutions when you don't consider invariance by rotation, but invariance by translation. So there are strips, right? A strip is invariant by translation. And so in this case, you can find 2 points of bifurcations. So I took a strip. Since I periodize, I can consider just a compact patch, which is the fundamental domain that I repeat. And I look at the evolution of the upper and lower boundaries. And so it's like having two boundaries. So it's like the case of the annulus. So you have two bifurcation points for a given symmetry, and they are given by this expression, provided that you push the symmetry large enough. Also in this work, they have to push the symmetries. And W here is the so-called Lambert function, which is the inverse of this function. Okay, so this was for Euler equations in the plane, in the disk, and in T cross R. But you can ask for different models, for instance, the SQG alpha, where you don't have a logarithm this time as the singularity integrated kernel, but you have 1 over x to the alpha. modulus of x to the alpha. You can also consider not a logarithm, but modification of the logarithm by multiplication and addition of an analytic function. So a particular case is given by the quasi-Jastrowicz-Shallow-Water equations. You can also have Euler alpha equations, which is a model given in the literature also. And in R3, you can consider the 3D quasi-geostrophic model, which is basically the 2D Euler equation, but seen in 3D. So it has been done by Claudia, Taufik, and Johan. And you can consider also a multi-layer model. So it has been done by Zineb and Harun. Or the lake equation, which is a generalization of the Euler equation, where you want to describe the fluid, but taking into account that there is a bottom topography. So it has been done in collaboration with Harun also and Mohamed. And you can do it for actually general Green kernel. And there is a general theorem which generalizes most of the models here in 2D. So not the 3D models, but these ones are almost generalized. The result here is weaker, but it's really general. So it's really an impressive work. And you can do it also for not fluid equations, but I could apply this kind of theory to solve to find non-trivial patches, but of electrons, not of fluids. Okay. And for the I want to mention a work that we have done with Claudia and Zineb about Euler equation on the sphere, which is more relevant since we are living in a planet. So you consider a sphere, the sphere S2, and the sphere is rotating around the vertical axis at a constant speed gamma, gamma here. And you can define a notion of vortex patches on the sphere that we call vortex caps. So for instance, if you take two caps like this with a circular interface, this is the analogous of the unit disk. And you can bifurcate from this and find non-trivial solutions, which will rotate by bifurcation theory. And the bifurcation that you get is basically the one of the plane, the full plane, so the Bourbéa one, times the vorticity jump between the north and the south pole, because in these kind of equations, you have an additional condition, which is the fact that the integral of the vorticity should be 0. So you should have some constraints here. And gamma, which is just the rotation of the sphere. So these are the bifurcation points, and this is the kind of solutions that we get. Which are also invariant by 2 pi over m rotation around the vertical axis. So the motivation for this work, and actually also the motivation for all the previous work, comes from the observation in the world that some order structures appear in fluids. Like for instance, here at the North Pole of Saturn, you have an hexagon like this, which appears. Okay. So now I give some pieces of literature about the non-rigid motion. So what we called before rigid motion was just you take the initial domain and it doesn't change the shape in time. It's just a rotation of it, but there is no oscillation during the motion. You just take the initial one and it rotates. So for the non-rigid motion, the first result were given in the so-called quasi-periodic class, so which is a generalization of periodic motion. That I don't give the definition here, but you can imagine that you take not just one frequency, omega, but you take two frequencies, omega 1, omega 2, and you make these two frequencies play their role. And if they are not, for instance, rationally dependent, then the motion will we have a good good structure. So so this has been done for most of the model that I presented before. Especially the main one is due to Berti, Arsenia, and Masmoudi, where they proved the existence of quasi-periodic vortex patches near the Kirchhoff ellipses. But each time to apply this theory, you have to play with the parameter. We will see it in the second part of the talk, why sometimes you need some parameter. And you can take it directly from the equation. Here, there is a parameter directly in the equation, or you can take it from the geometry itself. Here was the aspect ratio of the ellipse. Near, so in the unit disk, you can play with the radius of the internal radial solution. For the annulus also, you can play with the internal radius. And in T cross R, you can play with the area of the fundamental domain. So for this, I have some numerical simulations, for instance, which are just the solution that you obtain at the linear level, but the one that you obtain at the non-linear level are epsilon perturbation of it. So I just draw these ones. So you see that in time, this is rotating, but there is an oscillation of the boundary. So this was for instance, the quasi-stereoscopic shallow water model. If you take a layer in the unit disk, you have quite the same stuff. And if you take the annulus, for instance, you have this. So you see that the motion here is not rigid. You have some oscillation of the boundary in time. And for the strips, you can have this oscillation of the boundary. And for the periodic motion, so not the generalization where you have several frequencies, but just one frequency. The first result is really recent and due to Zineb, Taoufik, and Nader in the leapfrogging motion, where you consider so the leapfrogging is in the environment. So in physically, what it is, this phenomenon is that you take, for instance, you smoke and you are able to create a ring like this. So there are some people who are who can do this. So you create a ring and you can create another ring. And actually, if so the motion will be a translation of the rings, and one will be so the motion will be that the one behind will get inside the other one, and they will exchange like this their position. Just I will put some light. So they proved it for the 2D Euler equations, considering the point vortex dynamics that I will explain later. And the second result in the periodic non-rigid motion is the one that I will present in the second part of the talk. So just to mention the point vortex dynamics in bounded domains. So now we move to a new kind of solutions, which are formal solutions to Euler equations, where the vorticity is located on points zk of t. So you have n points. You give a strength to the points, which is how much it rotates, and you look at the evolution of the points in time. So the dynamics actually is Hamiltonian. And so it's a finite dimensional Hamiltonian system. And the Hamiltonian is given by this, where GD was the green kernel. And RD is given by the KZZ, so RD of Z, where K was the smooth perturbation of the algorithm for the green kernel. And you can relate it to the so-called conformal radius, which is this quantity, which is important in geometry. And so this Hamiltonian system is integrable for n less than 3. So if you have 1 point, 2 points, or 3 points, it is an integrable system. So you can completely describe the motion like you have, you can completely describe the motion with a given quantities. But in general, this system is well posed due to the Cauchy-Lipschitz theorem. So the trajectories are well defined until that you have a collision. So there are some people who studied the collision of the point vortex system. Okay. So for instance, if you take in R2, we said you don't have the K, so you don't have this part. So it's just this part with the green kernel. So if you take 2 points, what you get is that you get just this system. So you see that the quantity of interest is the difference, Z1 minus Z2. And so if you introduce capital Z this quantity, then you see that the motion for 2-point vortices will be either a translation with uniform speed, u, or a rotation, according if this quantity is 0 or not, the sum of the strengths. So now we come back to the vortex patch. So I just finished with this, and then we will stop and and pass to the second part of the talk. So if you take, for instance, so here the 2-point vortices in R2, and you take, so you have behind the dynamics of a point vortex, okay? But it is, as we have said, a formal solution because it's some Dirac mass, so it's a measure, so it's not really in a good functional space. So it's a formal solution to the Euler equations. And you want solutions that are well defined, so vortex patches, for instance. So you take a patch located around these point vortices. So I will put a patch around this one, a patch around this one, and the motion will be driven by the motion of the point vortices, but the point vortices are not really here. They are like ghosts, and that they will drive the motion, but the real solution will be vortex patches. So 2 vortex patches together. So for symmetric pairs, so where you have gamma 1 equal gamma 2 or gamma 1 equal minus gamma 2, for instance, this has been done by Taufik and Johan. And the more general case has been done by Taufik and Zineb. So they found that you have a uniform rotation. So you take 2 patches and you have a uniform rotation of the 2 patches if you're in this case, and if you're in this case, you have a uniform translation of 2 patches. And you can compute explicitly everything. And the proof of this result is just an application of the implicit function theorem, because here you don't have a line of trivial solution. Basically, your trivial solution is the point vortex itself. So it's like, it's not a line of solution, it's just one solution. And so you can apply the implicit function theorem near to it to find a curve of solutions. And the curve of solution or the non-trivial patches. So you can find non-trivial patches which will translate or rotate. And you can have more complicated configurations where you don't have 2-point vortices, but for instance, point vortices located on the vertices of a regular polygon. So it's a work by Claudia. And you can have also the von Karman vortex streets. So these are the uniform translation of patches, which are rows of patches, like infinite rows of patches. So here you have the point vortex system that you can desingularize into vortex patches. Sorry, you have point vortices, yes, that you can desingularize in vortex patches, and you have a uniform translation. And the work of general configuration by Zineb and Mice. They could consider, for instance, nested polygons of point vortices that you can desingularize with a central one, for instance, and which will have a uniform rotation. And so here, for instance, at the North Pole of Jupiter, you have this kind of structure which rotate with a center vortex and surrounded by several vortices around it, located at a regular, at the vertices of a regular polygon. Okay. So I just mentioned that there are other approach that the one that I described. So the one that I described from the beginning is that we use this equation, the vortex patch equation, to tackle the dynamics of the boundary. But actually, I should mention that vortex patches are actually so if you take the kinetic energy of the fluid, the vortex patches are the maximizers of the kinetic energy. So if you take a maximizer of the kinetic energy, you can prove that it is a vortex patch actually. So you can use variational approach to find non-trivial solutions. And it's a whole aspect of the theory that I just mentioned here, but there are a lot of people, especially the Chinese community, who are pretty specialist in this kind of techniques. So for this first part, so which was an introduction to the vortex patch, to the periodic vortex patch theory, so I will stop now and we will pass to the second part later. Thank you.